This lecture covers the time complexity analysis of divide and conquer algorithms. Here's the roadmap of what we will cover. In this lecture, we will cover a new generalized approach to analyze time complexity of divide and conquer algorithms, the Master Theorem. We will also revisit the recurrence tree method so that you can compare the two generalized approaches to time complexity analysis of divide and conquer algorithms. We will use the merge sort algorithm as an example to start our discussion. On the screen, you can find the pseudocode of the merge sort algorithm. In case if you don't know how merge sort works, let's cover the basics of this algorithm first. On a large picture, merge sort is a classical divide and conquer algorithm. It recursively divides the unsorted array into two smaller subarrays until each subarray has only one element. This is the divide step. After that, it compares elements from the two subarrays and merges them in sorted order. This is done recursively, building up the sorted array from smaller sorted pieces. This is the conquer step. After merging all the subarrays back together, the entire array will become sorted. This is the combine step. Different from the insertion sort that we covered previously, merge sort requires additional memory for the temporary arrays that are used in the divide and merge process. Now, let's take a look at the code to help you get a better understanding of how merge sort works. Merge sort takes one parameter A, which is a linear data structure like an array. The first line is the condition for everything that follows. The condition says that the length of the array needs to be bigger than 1. Otherwise, don't run this algorithm at all. Of course, if an array has a size of 1, it's already sorted. Only when an array has a length that's bigger than 1, merge sort can offer some help. The merge sort algorithm can be divided into 3 code blocks. The first block does the divide. The second block does the conquer. And the third block does the combine task. Let's hide block 2 and 3, so we can focus only on the first block. The first block of code starts by finding the middle index of the input array. If you divide the input array by that index, you will have the left half and the right half. After that, this block of code makes 2 deep copies of the left and the right halves. Note that it's a deep copy. In other words, the variable left half and the right half here refer to 2 totally different arrays from the left part or the right part of the original input array. Okay, but the left half will end up having the same elements of the left half of the original input. The same thing can be said for the right half. It will eventually have the same elements as the right half of the original input after you finish running the first block of code. Any changes to left half, I'm talking about the variable, won't affect the original input and vice versa, because it's a deep copy. The same thing can be said, of course, for the right half. Okay, that's the first block of code, the divide step. The second code block is a recursive call on 2 deep copies, left half and right half, that were generated from the first block of code. You can think that after the recursive call of merge sort being applied to the left and the right half, both of the 2 deep copies would be fully sorted. That's all you need to know for now, and we won't look underneath the hood yet. We will revisit this soon. Now, all you need to know is that after you run the second block of code, both the left half and the right half would be fully sorted. Let's get a good understanding of what the third block of code does first. The third block assumes one thing, which is that the left half and the right half are 2 fully sorted arrays. Then it moves on to merge the 2 sorted arrays into one big array by using 3 pointers, I, j, and k, to track the merge process. The first while loop does the merging by comparing the elements pointed by I in the left half and pointed by j in the right half. and copying the smaller element into A, the original input, at the position of the index k. When this while loop terminates, it's possible for either the left half or right half to have some elements that were never examined or compared or used in this process. That's where the second and the third while loop comes into play. The second and the third loops, they check if there are any remaining elements in either left half or right half that need to be copied directly to A. If so, they will do accordingly. You may notice that the merged elements are directly placed into the original input array, capital letter A. That will overwrite the existing elements, of course. But since left half and the right half have all the original elements, the existing elements in A no longer matter, and the overwriting would be fine. Let's walk through an example to make sure we are on the same page about this block of code, about how the merging would work. Okay, as you can see on the screen, the left half and the right half are the two sorted arrays. A is the original input array, and will be used as a vehicle to store all the sorted elements. This process will lead to the original elements in A being overwritten. The original elements in A no longer matter because they have been stored in both left half and right half. As a result, we will hide them in our visual to avoid distractions, like this. Okay? The I, J, and K are the 3 pointers that are all initialized to 0. Okay? Index zeros. They are used to track the process of merging left half and right half into A. You will do so by comparing the elements pointed by I and J, and put the element that's smaller into their K points in A. In this example, as shown on the screen, I currently points at 1. J currently points at 2. Since 1 is smaller than 2, it will place 1 into the index of K, which is 0 in A. After this, it will move the pointers from either left half or right half if you have copied this element to A. In our example, we copied 1 to A, and 1 comes from left half, so we move I rightward by 1 step. Besides that, we would always move K rightward by 1 step, so that it can point to the next vacancy where you can place an element in without causing troubles. So we move both I and K rightward by 1 step. Then, you would continue the comparison process. The element pointed by I right now is 3, and the element pointed by J is 2. Since 2 is smaller, it would copy 2 into A at the index of K, and move both pointers J and K rightward by 1 step. Okay, the comparison would continue. The element currently pointed by I is 3, and the element pointed by J is 5. Since 3 is smaller, it would copy 3 into A and place it at the index K. After that, you move the index I and K rightward by 1 step. The next comparison is between 4 and 5. Since 4 is smaller, it would place 4 into A at the index K. After that, you move the index I and K rightward by 1 step. The next comparison now is between 7 and 5. Since 5 is smaller, you would copy 5 into A at index K, and move both J and K 1 step rightward. The next comparison is between 7 and 8. Since 7 is smaller, you would copy it to A at K, and move both I and K rightward by 1 step. Now you have depleted the left half, since I is bigger than the length of left half. So the comparison is over. The first while loop ends. Yet, you still have some elements in right half, as J is pointing at some element in the right half. So you can copy everything starting from J till the end in the right half directly to A. That's how the merging process works. Now you know what all the 3 code blocks do. let's focus our attention on the second code block again, the recursive call. To make things easier to navigate, I will replace block 1 and 3 with comments, like this. So now there's only one thing that I want to bring to your attention. The recursive call are placed in the middle of the function definition. We know that code gets executed from top to the bottom, from left to the right. The first code block does the divide by making deep copies of left half and right half subarrays. The third code block does the combine task by merging two sorted subarrays back into one fully sorted array. If we execute merge sort on a given array, like what you see here on the screen, the order of execution will eventually lead to a visual like this. Okay? A good exercise to test your understanding of the execution order is to figure out whether the step A or step B firstly gets executed. Both A and B are highlighted in the visual. The answer is that A gets executed ahead of B, because code always gets executed from top to the bottom, from left to the right. So the recursive call on left half will keep triggering other recursive calls on their left halves until the subarray size becomes 1, because they get executed sooner than any other recursive calls on any right half based on their order. In short, you will keep dividing, but your focus is always on the left half until you have a single element array. Then it will trigger the execution of the first merge sort on the single element right half, which is 8. After that, it will reach the first combine step for the two element array, 5 and 8. And the combine step, or say merge step, merge sort will sort the two elements in increasing order. The two elements are already in the right order, so you won't see any changes here. Then it will move to execute the merge sort on the right half with two elements. In our case, that's 3 and 1. Then the same story will happen. It will make deep copies of 3, the left half, and 1, the right half, and then combine and sort the two elements into 1, 3, like this. Then the combine step on the 4 elements, 5, 8, 3, and 1, will be triggered to merge the two element arrays. It will end up with a sorted 4-element array, like this, 1, 3, 5, 8. The execution order on right half of the original input will be quite similar. You will start with a series of triggering of the merge sort on all the left halves until you have a single element, which is 4. Then the merge sort will be triggered on the right half with a single element 10. Then the combine step, or say the merge step, will happen to the two element array, 4 and 10. That said, they will be sorted. Well, they are already in the right order, so you won't see any changes. Then merge sort will be triggered on the two element array, 2 and 7, before you end up with two single element arrays, 2 and 7. Then you will merge them, or say sort them into 2 and 7. After that, you will combine, or say merge the two element arrays, 4, 10 and 2, 7, so it will become 2, 4, 7, 10. In the end, you will finally combine the two 4-element arrays. I'm talking about 1, 3, 5, 8. The other array is 2, 4, 7, 10. They are already perfectly sorted, so this step will sort the original input array, like this. Then you are done. That's a complete breakdown of the execution order of the merge sort being applied to an 8-element array example. So in summary, merge sort will keep dividing until you have a set of single-element arrays. Then merges them back into a set of 2-element arrays, then 4-element arrays. The process continues until you have a fully sorted array of the same size as the input array. The merge process also takes care of sorting. Now you know how merge sort works, let's discuss its time complexity analysis. In the part 1 lecture, we learned recurrence relation and recurrence tree method that is used to analyze the time complexity function and the upper bound of divide and conquer algorithms. Let's revisit them here in the context of merge sort. Let's start with a simple question. What's the recurrence relation of merge sort? Assuming that we have called this function, this merge sort algorithm, on a given array A, like this example, the time complexity at this step, when we call merge sort with this particular argument as A, is Tn, right? We also know that Tn is equal to the sum of the time the 3 code blocks take to be executed. Well, last thing that we know is that the second block of code triggers a recursive call on data of half input size in comparison to A. So each recursive calls will take t of n divided by 2 time. It's the same function of merge sort being called on half of A. There are 2 of them, so the second block of code takes 2 multiplied by t of n divided by 2 time, like this. So we are halfway from establishing a relationship between Tn at the current step and the next step when recursion calls are triggered. The remaining part of this recurrence relation is to figure out the time the first and the third block of codes take. The first block of code has 3 steps. The 3 lines are about making deep copies of the left half and the right half of the original input array, which takes c multiplied by n time to do. You can approach making deep copies by traversing through the whole given input array. So it's going to be c1 multiplied by n, where c1 is a constant number. What about the third block of code? The first 3 lines initialize I, j, and k to 0. They take constant time to run. The first while loop takes the same number of iterations as either the length of the left half or the right half, whichever is smaller. After that, either the second or the third loop would get executed, traversing the elements that were not examined in the longer one between left half or right half. The length of the left half is roughly n divided by 2. Same for right half. The 3 while loops are placed one after another, so executing them takes maybe c2 multiplied by n time, which is in proportion to the input size. So that's c2 multiplied by n, where c2 is another constant number. Now you have a recurrence relation between Tn at the current step and the next step t of n divided by 2 when the recursive calls are executed. We can actually simplify this equation a bit by combining c1 and c2 and replace them with a single letter c, which is another constant number. So the relationship can be simplified to Tn equal to 2 multiplied by t of n divided by 2 plus c multiplied by n. Okay? With the recurrence relation set, we can move to apply the recurrence tree method to figure out the actual time complexity function and its upper bound. Before we do anything, I need to remind you that the recurrence relation is composed of 2 parts, the work done in the current step and the work done in the recursive call. The time it takes to get the work done at the current step is c multiplied by n. Okay? The recursion takes 2 multiplied by t of n divided by 2 time. Using the recurrence tree method, we will list the subproblem size and the time it takes to solve the work at each step corresponding to the problem size in 2 columns side by side, like this. The current problem size is n, and the time it takes to solve the work at the current step outside of the recursion is c multiplied by n. So we can list them in this table like this. In the next step, the recursion is triggered on half of the input size, both left half and the right half. So the problem size becomes n divided by 2 for the left half and n divided by 2 for the right half. Since there are two of them, we will list them both. Merging for both left half and the merging for right half are both c multiplied by n then divided by 2. Since there are two of them, the total time will be the sum of the two, which is also c multiplied by n. In the next step, step 3, it will trigger for merge sort on further half the input sizes. Each of those arrays will be of the size as n divided by 4. The merging for those arrays will be c multiplied by n then divided by 4. Since there are 4 of them, you will need to add them up to derive the total time it will take to solve the work at this step. In the end, it will have another c multiplied by n time in the right column. The next step will be similar. It will trigger merge sort on further half the input size. This time, that's n divided by 8. And the time it takes to merge each of those subarrays will be c multiplied by n then divided by 8. There are 8 of them, so the total time will be the sum, like this. You may have seen a pattern here. Regardless of the problem size, the total time to address all the work at that particular step is always going to be c multiplied by n. The process will continue until the problem size becomes 1, like this. So now, to figure out the total time it takes to execute a merge sort, you will need to add all those total merging time together. To do that, you need to answer a key question. How many of c multiplied by n are there? If you look at this tree structure that you have developed, this becomes a familiar question. How many times can you keep dividing n by 2 until it becomes 1? The same equation that you have solved. Okay? If you apply logarithmic to both sides, you will have the answer to the question. It takes k step to keep dividing n by 2 until it becomes 1, and k is equal to log n. That said, there are log n number of c multiplied by n, so you can calculate that Tn is equal to c multiplied by n, then multiplied by log n. The constant number c doesn't really matter, especially when it comes to calculating the upper bound. So the upper bound is n multiplied by log n. Now you have figured out the time complexity and the upper bound of the merge sort via the recurrence tree method. Let's move to discuss a different generalized approach to derive the time complexity analysis for divide and conquer algorithm, the Master Theorem. So what's the Master Theorem? The Master Theorem is a powerful tool that's used to analyze the time complexity of recursive algorithms, especially for divide and conquer algorithms. It provides a way to determine the asymptotic behavior of a recurrence relation. In other words, given a recurrence relation, the Master Theorem helps you find its bound. The definition of the Master Theorem is presented on the screen. Let's digest it bit by bit. I'm going to hide the 3 different conditions, so we can focus on explaining the context first. Okay? Given a recurrence relation expressed as Tn equal to a multiplied by t of n divided by b plus fn. A multiplied by t of n divided by b represents the amount of time the recursion takes. A represents the number of subproblems, and b represents how the problem size is divided at the current step. Fn is a term representing the amount of time required to perform the work at the current step outside of the recursion. Recall the recurrence relation of merge sort we just covered. It can be expressed like this. In this case, both a and b are 2, and c multiplied by n is the fn for the merge sort. The first two represents how many subproblems are there at each step of the recursion, and the second two represents how the problem is divided at each step of the recursion. And C multiplied by N represents how much time it takes to do the work at each step outside of the recursive call. Particularly, the majority of the work is merging. There are three conditions specified in the Master Theorem based on the comparison between the growth rate of Fn and n power to the log base b of a. If Fn grows slower, then you have the first condition. If Fn grows at the same rate as n power to log base b of a, then you have the second condition. If Fn grows faster, and Fn is the dominant growth term in comparison to the recursive term, you have the third condition. Okay, let's dive into these different conditions. In the first condition, when Fn grows slower, the tight bound of Tn is theta n power to log base b of a. In the second condition, when Fn grows at the same rate as n power to log base b of a, the tight bound of Tn is theta n power to log base b of a multiplied by log n. In the third condition, when Fn grows faster than n power to log base b of a, and Fn is the dominant growth term in comparison to the recursive term. Yes, that's what this regularity condition specifies. Then, the tight bound of Tn is theta of Fn. To use the Master Theorem, you will start by comparing the growth rate between Fn and n power to log base b of a, and determine which condition you are working with. After that, all you need to do is to plug in whatever the Master Theorem says. For example, this is a recurrence relation of the merge sort. To determine which condition this recurrence relation falls into, we will list the corresponding A, B, Fn, as well as the growth rate comparison between Fn and n power to log base b of a, like this. As you can see, A is equal to 2, B is equal to 2. Fn grows at the same rate as n power to log base 2 of 2, which is n power to 1. So the recurrence relation of merge sort falls into the second condition. Okay, because Fn grows at a linear time, and n power to 1 also grows at a linear time. So the tight bound of the merge sort algorithm can be expressed as theta of n power to log base 2 of 2, then multiplied by log n, which is n log n. Let's see another example of the application of the Master Theorem, the binary search. The recurrence relation of the binary search is shown on the screen. We learned this from the Part 1 lecture. To apply the Master Theorem to figure out its bound, we will list A, B, and the growth rate comparison between Fn and n power to log base b of a, like this. In this case, A is 1, B is 2, log base 2 of 1 is 0, so n power to 0 gives you a constant number 1. So Fn also has a constant number C, grows at the same rate as constant number 1. As a result, you have case 2 again. So the tight bound of Tn can be expressed as is specified in condition 2, which is just a log n in the end, because the power of n is log base 2 of 1, which is 0. N power to 0 gives you a constant number 1. When you multiply log n by 1, it's still log n. That's the second example of the application of Master Theorem. As you can see, its application is more blunt and direct than the recurrence tree method, but you will need to either memorize it, or you can refer to its definition somewhere if you want to use it. In this lecture, we used merge sort as a divide and conquer algorithm example to cover a generalized approach to time complexity analysis on all divide and conquer algorithms, the Master Theorem. We also compared the Master Theorem to the recurrence tree method.